Welcome back. I'm Brodie Pearson and I'm going to be leading the final 3 tutorials of today's Climate Modelling Day, and I'll also be leading the Future Climate Physical Basis Day at the beginning of next week. Now in the next couple of tutorials we're going to be continuing our theme of today, which has been to add complexity to a radiative equilibrium model to make it more realistic. And in this tutorial number 5, we're specifically going to be adding in elements of the vertical structure of the atmosphere to that model. Now to recap, in the last tutorial, you were adding complexity to the radiative equilibrium model by going from an albedo that's described by a constant parameter to one that varies with temperature to represent the changes in ice cover on Earth's surface as temperature varies. But even with this added complexity, this model just told you about the surface temperature of the planet. Now we know that the atmosphere has vertical complexity too, for a couple of reasons, and in this particular tutorial we're going to be adding in the elements of gases that vary with height and their different radiative properties. So far you've been modelling the global mean surface temperature assuming that the atmosphere is homogeneous, that is the same everywhere and at all heights, and the atmosphere just absorbs outgoing long wave radiation with a fraction governed by a single parameter, tau, transmissivity. But we know the picture is more complicated than that. You've seen a plot like this one here which shows the fraction of radiation absorbed by the atmosphere as a function of wavelength of that radiation. And there are many parts of the outgoing long wave radiation that are absorbed by atmospheric gases. But there are also parts of the incoming solar radiation, the yellow region on this plot, that are absorbed by atmospheric gases. And so this is an extra element of complexity that we didn't have in our previous model. And these gases also vary with height. So for example, ozone, which is shown in the plot on the right as a function of altitude, is primarily concentrated in the stratosphere, so the upper atmosphere. And there isn't much ozone near the surface. And this ozone is very important for absorbing incoming solar radiation, particularly the highest frequency or lowest wavelength light in the UV bands. Other gases are more concentrated near the surface, and others are distributed quite evenly throughout the atmosphere. And unsurprisingly, this absorption of different parts of the incoming and outgoing radiation spectra at different heights leads to variations in temperature with height. And so we know that global mean temperature varies with height. This is a plot shown on the right showing that global mean temperature decreasing with height until you get to the stratosphere where it increases with height. Now this is a skew-T plot, which is a common way of plotting atmospheric properties as a function of height. Instead of height on the y-axis, there's pressure, and pressure decreases as you go up in the atmosphere. And then it's called a skew-T plot because the temperature is actually represented by these slanted or skewed lines going up towards the top right. And we'll talk about this kind of plot more in the tutorial. But the important thing for this tutorial is the radiative equilibrium model can be extended to predict temperature as a function of height. And when we do that, we go from having a 0-dimensional model that just tells us about one parameter, the global mean surface temperature, and it becomes a 1-dimensional model, something that tells us about how this temperature varies with height, which is our dimension in that problem. And we're going to do that by adding 2 extra bits of physics. We're going to be adding in multiple layers and distinct gas concentrations within these layers, so things like ozone and water vapor being distributed differently with height. And we're going to add in the fact that these different gases absorb different parts of the incoming and outgoing radiation spectra. So I will leave you to get on with that tutorial, and I will see you again shortly.